This video is on molecules with multiple chirality centers. This is where things get a little complicated. So the maximum number of stereoisomers is equal to 2 to the power of n, where n is the number of stereocenters in your molecule. So 2 chirality centers leads to 4 possible products. Theoretically speaking, we would have the RR and the SS, which are enantiomers, and the RS and the SR compounds, which are both also enantiomers. Now the RR and the RS, though, are not enantiomers anymore, but they are different. So we need to learn a new term here. These are diastereomers or diastereoisomers. These are non-mirror images, yet they are still technically the same constitutional isomer. A real-life example of this would be ephedrine, seen here with its 2 chiral centers. We'll notice that the RS and the SR stereoisomers have a specific rotation of 6.3, and they have melting points at 40 degrees Celsius. However, the diastereoisomers, RR and SS, which are enantiomers of each other, have a specific rotation of 52 and a melting point of 118 degrees Celsius. Sometimes multiple chirality centers can cause symmetry. For example, this tartaric acid. It should have 4 stereoisomers as it has 2 chiral centers. Now if we look at them, we have the SS and the RR, both with specific rotations of 12 and melting points between 169 and 170. However, the RS and the SR actually are the same because they have a line of symmetry. They have a specific rotation of 0 and a melting point of 159 to 160. The fact that they are the same means that we don't even need to draw 2 of them. There are only 3 stereoisomers of tartaric acid. This one, with its symmetry, is referred to as the Meso stereoisomer. Because of this symmetry that may arise and cause mesostereoisomers, the question of how many stereoisomers does each of the following compounds have becomes slightly more complicated, as you have to be aware of this symmetry. However, for example, this molecule here clearly has no symmetry, whilst this molecule here seems to have some symmetry, so we might want to be careful and check whether there is a meso stereoisomer or not. How do we check? We draw them out. And as we can see, these 2 seem to be the same. So we would only have 3 stereoisomers for this compound. Now you have a go. Locate all the stereocenters on the remaining molecules and draw all stereoisomers to confirm that your number of predicted stereoisomers is the same or if it's different, and mesostereoisomers are present. In the interest of time, we'll discuss these in class.